Welcome to Basics of Finite Element Analysis Part 2. This is the 5th week of this course and today is the 4th day of the week. So, we will continue to develop the finite element formulation for the 2-dimensional single variable problem, and today and maybe in the next class what we will focus upon is the method to develop interpolation functions for this problem formulation. So, we will work on figuring out how to develop interpolation functions in 2D. Okay. Now, so what does that mean? So, we had said that the displacement or the variable u, we can approximate it as uj psi j x and y, where j could be 1 to n, and here uj are unknown constants psi j are interpolation functions for jth node. Okay, so the interpolation function psi j represents the function for jth node. So, what we are interested in figuring out is what is the nature of this psi j, because uj is a constant, so we do not have to worry about it. What is the nature of psi j? How do we figure that out? As we are, excuse me, so let us call this equation 1. As we are developing this these functions, we have to make sure that some important conditions are met, and we had discussed these conditions also when we were doing our 1D formulation. So, the first thing is, so important conditions. So, the first one is that whenever we pick up psi j, we have to ensure that we pick up psi j in such a way that u of x y, which is the actual unknown variable, has sufficient differentiability. Okay, it should have sufficient differentiability. So, what does that mean? Because so in this formulation, in the weak form, the differentiability requirement is of the first order, right? It should be sufficiently differentiable at least once. If we had used the strong form, which would be this form, then the differentiability would be of second order. So, we have to pick psi j's in such a way that u is sufficiently differentiable. This is important. The second thing is that the psi j will be some polynomial function, right. So, we have to pick up psi j in such a way that u e of x y should be a complete polynomial. That is, all terms up to highest order must be included in UE. Okay. So, what does that mean? So UE could be, UE would be a polynomial function. Example, UE xy is equal to a plus bx. Is it a complete so this is a function of x and y. Is it a complete function? No. Why? Because I have not included the yth term in it, the y term in it. So a plus bx plus cy, this is a complete polynomial. Another example, UE xy equals a plus bx plus dxy. Is it a complete polynomial? No, because I am missing the y term. So, a complete polynomial would be a plus bx plus cy plus dxy. This is a complete polynomial. One third example could be UE xy is a plus bx plus cy plus dxy plus e x square. This is not a complete polynomial, but I can make it a complete polynomial this is a complete polynomial. Okay. So, it has to be complete polynomial, otherwise our results will be inaccurate because they will be skewed in one particular dimension strongly, right. So, that is there. The third thing is that all polynomial terms should be linearly independent. So, they should be linearly independent. They should not be linear combinations of two things. So, I cannot have a plus bx plus cx, because bx plus cx, they are all not linearly independent. Okay. So, that is important thing. So, with this background, let us look at some functions. So, let us look at linear UE of x and y. So, we are still not talking about interpolation functions. We are right now on UE, not on size, but from U we will go to size later. So, if U is linear, then the simplest expression would be constant C1 plus C2x plus C3y. Okay. C1 plus C2x plus C3y. So, here C1, C2, C3 linearly independent constants, and this is linear in x and y, and C1 and they are unknowns. They are unknowns. So, we have three unknowns, and if we have three unknowns, then we have to know, to find them out, we have to know conditions at three different points, right. So, we have to know conditions at three different points, which means this type of an expression could correspond to this type of an element. Someone can also say that to find these three unknowns, So, this is node 1, 2 and 3. So, this is option A, this is option B. Here I have 1, 2 and 3. Here also there are 3 points. If I know 3 conditions at 3 locations, and in option A I have conditions in 3 locations, but then I can find out C1, C2, C3 for case A, but I may not be able to find it for case B. Why? Because these 3 conditions at 1, 2 and 3, they are not linearly mutually independent. Okay? Because if I know condition at point 1, if I know condition at point 2, condition at point 3, condition at point 2 is somewhere, an interpolation of that, right. So, it can be a combination of 3 and 1, but in case of case A, condition at 2 is not a linear combination of 1 and 3. Okay. So, if I have this type of a function such that the displacement over the element is varying in a linear way, then that corresponds to a triangular element with 3 nodes, triangular element with 3 nodes. Another example, so this is first case. Now, let us look at second case. Linear UE and x and y, and this is equal to C1 plus C2x plus C3y plus C4 xy. So, here I have 4 constants, 4 unknowns C1, C2, C3, C4. To find out C1, C2, C3, C4, I should know conditions at least 4 points. So, what could those 4 points be? So, these 4 points could be vertices of a quadrilateral, or they could be for a triangle, or they could be for a line. So, once again I have case A, case B and case C. Now, if we consider case C, the values of u at 2 and 3, if it is a linear variation, then it is not independent of, it is not linearly independent of 1 and 4, right. So, this is not possible, a valid option. The same thing is true for case B also, where point 2 is located at the centroid of the triangle. So, the 4th node is located at the centroid of the triangle, but here also the same thing is the logic which we used in case C, it also applies for case B. If you do the mathematics, you will find it out. So, if I have a function UE which is equal to C1 plus C2x plus C3y plus C4 xy, this type of variation of U can exist on a 4 noded quadrilateral. Third case, we consider a quadratic polynomial. UE So, this is a quadratic polynomial, but we are seeing that the weight on x square and y square is same. So, we have violated our own condition that these weights should be independent of each other, right. Earlier we had said all polynomial terms should be linearly independent. Here the weight on x square and y square is not same. So, we have violated our own condition. This type of function, you could think it could exist on a square or a quadrilateral with a mid node, but when you apply this on this thing, you will again see the compatibility issues. So, this is not a valid option. So, this is that. So, this is an incomplete quadratic polynomial. So, this is not a valid option. Fourth case could be a complete quadratic polynomial okay. So, here UE of xy equals C1 plus C2x plus C3y plus C4xy plus C5x square plus C6y square. So, here there are 6 unknowns. To know these 6 unknowns, we have to know conditions at 6 different points, right, and this is, there are square terms in the expression. So, one possible topology, or actually the only possible topology, would be this. Here the variation of u from 1 to 3 is not linear, it is quadratic. So, I need conditions at one additional point. Same thing is true for 3 to 5. The variation of u from 3 to 5 is not linear, but it is quadratic. So, for a quadratic expression, I need one additional data at one additional point. Same thing on the third edge. So, this is a quadratic triangle. The first triangle which we had discussed was a linear triangle. So, like this we can develop quadratic, quadrilateral and higher order elements in this way. So, this completes our discussion for this particular lecture. In the next lecture, what we will do is we will develop the interpolation functions for a linear triangular element. And what we have discussed today are different types of elements. So, we have a linear triangular element, then we have a first order a linear quadrilateral, then we saw that this incomplete quadratic polynomial does not give us a valid element. Then finally, we have, if we use a quadratic polynomial for u, then that will work if we use a quadratic or a second order triangular element. So, this completes our discussion for today, and we will continue the discussion on interpolation functions tomorrow as well. Thank you.